Good afternoon, everyone. Only one day left to go after today, and then we will leave you for the exam period. I hope you're all feeling relatively rested and prepared as we go into SWOT-VAC, and I will leave you hopefully in a state of rest, knowing that we don't have too much more material to cover from this class. So from here, it's mostly sit back and relax. We have two more data structures and algorithms to cover. The first of these are going to be priority queues, for which we will look at an implementation using arrays, and that'll give us our final sorting algorithm for the semester. And we're also going to look at hash tables. If you remember from yesterday, we were looking at a variety of different sorts of strategies for developing algorithms. We had generate and test, and divide and conquer, and today we'll look at a few more. Today's strategy that we're going to kick it off with is simulation and randomization. This will give us another way to process data and try and come up with a function that approximates or gives us a good enough answer to the problem in question. So there's going to be a number of different types of questions for which this works. There's not going to be a randomized algorithm for every type of problem out there. But for the algorithms and for the problems for which this solution type does apply, we're going to see that it can both improve on our efficiency for what a deterministic algorithm might be, as well as give us tractable solutions for problems which otherwise might have been too inefficient for us to be able to solve using our regular algorithms. My research is actually in random number generation, which is key to this type of algorithm. In fact, without good quality random numbers, you both don't have computer security and you don't have these randomized algorithms. So it turns out that randomness is quite an important and powerful tool for us to use in computer science. The only thing is we have a bit of a challenge in that computers don't know how to be random. If I go up to the computer and I say, "Computer, give me a random number," how is the computer meant to do that? The computer doesn't have like a brain inside it that can say, "Oh, I'm going to pick a random number out of all the possible numbers and it's going to be 42. There's no built-in source of randomness inside most computers. And so we have to come up with a way of at least tricking the computer into producing a random number. This might be by using things that are very unpredictable. So one way that we could do this would be by taking in a lot of input that is unpredictable from the world, such as when you turn the computer on, what are the different times that you move the mouse and how do you move it? That's not truly random because you were controlling it and that was not completely outside the scope of predictability. If someone knew you very well, maybe they could guess your mouse movements. But it's close enough to random that for the most part it looks really different from an organized set of numbers that one might consider. But if we combine that source of randomness with another source of randomness, let's say the time of day the computer was turned on, and combine that with another source of randomness, such as the different times in which the hard disk inside your computer was accessed, we start to get something which is truly unpredictable, even for someone who knows a few different things about you or about your computer. What we then do is we mix up the randomness, and we'll talk about that in tomorrow's lecture of how we do that, using something called a hash function, typically. And we put that all together, and then we are able to extract random numbers from our mixed source of all the randomness that we've been collecting, or all the pseudo-randomness. And we call this process pseudo-random number generation. Because it's not truly random, we know some of the ingredients that have gone into it, and they're not really random. But to an observer looking at the stream of numbers, there's no way to tell if these numbers were actually drawn from true randomness or were drawn using this procedure, because there's no way to guess what this procedure is going to put out. And that's, if you want to learn a bit more about that, I write and teach quite a lot about it in my other class in computer security and also in my research papers. But this randomness can be useful too for practical purposes.
Yeah. Sometimes I get so mad, there's no controlling me. My thoughts get so bad, I'm like, I might grab a bat, I don't know. My wrath, my blood boils over like, oh God, here goes. I lost all feeling from my head to my toes. You said some shit that I can't let go, so just stay tuned for the rest of the show. So have you ever felt betrayed? Switches how you see things, realize something needs change. Cause I know you got me f***ed up, let me show you what's up. Cause enough is enough. I'll take a face full of pavement just to make a statement. I know there's no turning back. Oh God, adrenaline wasted, so mad I can taste it. I know there's no turning back. I'll do what it takes, I ain't making mistakes like that. I'll bleed on your face just to make you go take it back. I'll lose my shit, I go crazy when I'm mad. And now you go wish you would shut the fuck up real bad. And now that I'm gone, yeah, I know there's no turning back. And now that I'm gone, yeah, I know there's no turning back. I'll take smoke, I'ma poke a hole through you, choking's overdue. Come at me and you won't get any older, dude. Crack your holder too. Heating up inside of me, blood so violently. Thanks for trying me. Now it's finally time to see how this ride.
What you just saw in this video that I had up over here was a method to calculate the value of pi starting from only the piece of information that pi is equivalent to the ratio of the circle to the larger square within it. And we knew that that was the case because we did that little derivation over there. It was equal to 4 times that ratio between the area of the circle and the square in which the circle was inscribed, assuming that the radius of the circle was r and was the same distance as the midpoint from the inside the square to the outside of the square. Then, if we can actually generate really good quality random numbers, we throw a bunch of darts into our square, and we see how many of them land inside the square, how many of them land inside the circle. If we calculate the relationship between the number that landed in the square but outside the circle and the number that landed inside the circle, we get that ratio between the two that we're looking at, multiply it by 4, and we're able to compute the value of pi. And this is a somewhat surprising result because we didn't feed in any information about what pi is other than the fact that it's 4 times this ratio, and then use randomness in order to actually calculate what it is. This may be surprising, but it is a good example of the way that randomness can be used to generate fairly important solutions to problems that are otherwise tricky. And for a computer, figuring out the exact value of pi isn't necessarily a natural operation. There are a number of different ways to define pi, but a lot of them involve either expansion of something like a Taylor series or other more complicated methods. But with this random method, we can do this fairly simply and get pretty high accuracy with a relatively small number of computations for the computer. 200,000 points, not so much when you're talking about the CPU of our computer, and we'll actually see in a minute when we run some of this code that does a similar thing, quite how easy it is to do, and quite how quickly we can generate a good value for pi. The code that I'm going to show you today is different from the code provided with the book. I've made a few small changes because to improve the quality of the randomness, but both the programs are equally as applicable. I've just modernized the version in the book a little further. C does have built-in functions for producing random numbers. Historically, they weren't that great, and if you're not careful, you can still end up using the wrong source of random numbers. And this could be dangerous for a number of reasons. So think back to earlier in semester, and we talked about the Diffie-Hellman key exchange protocol. And you might remember that as part of the protocol, both Alice and Bob generated their own secret random number. Why might it be a problem if the quality of the randomness that the computer is generating is not particularly high? Stephen, do you have an idea? We'll take the microphone to you in a second and we can figure it out. Here.
It's easier to crack the code.
Why might it be easier to crack the code if the source of random numbers is not high quality?
Because you can probably find out what the method it is.
Yeah, so let's say that in my method of picking random numbers is by looking at the time of day when I turned on my computer. Why might that be a problem for the security of the Diffie-Hellman key exchange algorithm?
Because the sample number isn't too big.
The sample size is small, and you know me pretty well at this point. What time do I get out of bed in the morning, more or less?
Probably 6, 7.
Yeah, about 7 a.m. And so if you were trying to figure out what random number I picked, what would be a good guess for it if you know my method is the time of day that I turned on my computer?
7:15, 7:20.
7:20 is leaving it a long time. You know, I'm a computer guy. It's going to be 7:01. I wake up at 7:01 the computer is on. So Stephen points out to us that if you have a low quality source of randomness, and you can therefore guess what the random numbers will be fairly easily, the strength of a security protocol that relies on the quality of the randomness and that relies on someone not being able to guess what these random numbers are is going to fall pretty quickly. So if Tarish is trying to break into my computer system and he needs to guess what my half of the Diffie-Hellman key exchange is, he substitutes into the protocol the number 701 for the random number that was generated. And if that doesn't work, he tries 702, 703, 704. And instead of having to pick all the numbers out of this very large possible set of numbers, say we're dealing with a 64-bit secret, instead of having to look at all the different 64-bit numbers, he can just start at 701, 702, 703 and pick from a very small sample size. So the quality of randomness is really important. And that's for a security protocol. Why might it also be important for something like calculating the value of pi? You want to give it to Warren?
If there's a low source of randomness, you won't be able to cover all the points in the square in the example.
So what do I mean in this case by high quality random numbers? What does that tell me about the distribution that I want of random numbers?
Equal distribution?
I want a uniform distribution of random numbers such that any one of the points in that square has an equal chance of being picked. Because if they don't have an equal chance of being picked and I'm biased with the extent to which I pick some of the points, perhaps my bias is that I'm more biased to picking points inside the circle than I am to picking points outside the circle. And if that's the case, my ratio is going to be off. And so it's pretty important that the source of random numbers that we choose is high quality. That said, even the old versions of C, when you produced random numbers using the built-in functions, they were generally high enough quality for you to use them for calculating the value of pi. But for a security protocol, you need an even better source of randomness because you're fighting against someone who's actively trying to break things. You're fighting against someone who's doing their very best to guess what the points were. And so it's not only enough that they be uniformly distributed, but they have to be uniformly distributed in a way that I can't guess what the next number that you're going to put out is going to be. Thanks very much, Stephen, Warren, and Tarish. Operating systems have also provided a source of random numbers typically. In Linux, this was known as urandom and dev-urandom, two different sources of random numbers. As of about 3 weeks ago, Linux has cleaned up their act. There is now only one place that you can get random numbers from in the Linux operating system, and it's also relatively high quality. So some of these concerns that we're talking about, which made up pretty much all of my PhD, are now lesser problems in the world, and so we can rest easy. That said, it's still important to know how to get and use these random numbers in your code. There are a number of mathematical and algorithmic challenges in generating these random numbers. We've discussed some of them so far. And it comes down to not only collecting the randomness, the pseudo-randomness for us to feed in, but then in how we mix it together, and then furthermore, in how we ensure that the distribution of the random numbers that we're getting at the end of this process is uniform or uniform enough. With that, we're ready to take a look at some code that implements this Monte Carlo approximation method. And we'll talk about what a Monte Carlo approximation method is in a minute. So there we go. The bulk of the code is relatively simple. We have two values, xp and yp, and I'm going to fill them with randomness using this random function. The reason that I'm doing this funny thing over here and that funny thing over there is because the random function does not actually generate enough randomness to fill a 64-bit integer. And so what I'm doing is I'm treating the 64-bit integer like two 32-bit integers. I fill the first 32 bits, and then I fill the second 32 bits. And there's a little hack here to make sure that the last bit is also randomized. I wasn't able to figure out why that last bit wasn't getting randomized, but if you are able to figure it out by looking through the code, let me know. Then what I have to do is this has generated random integers, and so I need to convert them to floats. And the way to do this is fairly complicated. So for the time being, I'm just going to leave this here. But essentially what I'm doing is taking 11 of the bits and filling them in, remember how floating point numbers have 2 bits, the mantissa and the exponent, and so I'm filling it into the mantissa rather than the exponent over there and accounting for that. I then have my circle, which is given by the equation x squared plus y squared. All of you have done hopefully some introductory maths, and so understand that well. And my x and my y were just generated from the random numbers I got. So now that we have the radius, we can tell whether the radius is inside the circle, whether the points generated were inside the circle or outside the circle. They're inside the circle if the radius is less than or equal to 1, and if that's true, increase count by 1. And then here I just have some code that after every, what have I said here? After every 1 million iterations, print how many iterations you've done and print the value of pi that you were able to generate. Let's give it a run. So if you remember, I talked about this process of putting in some randomness into the random number generator in the first place. Now, one of the interesting questions is what happens if I don't feed it into the random number generator? And, oh, I know what's probably happened with this code. It's using an old version of it that wasn't uploaded. We'll have to fix that later. Yeah, if you don't seed the random number generator, if you haven't fed in appropriate randomness to it, you're going to get a random number generator that isn't really random. And while that might be okay if you're not using this for a security protocol, as long as you're drawing from a uniform distribution, that's going to be all right for estimating the value of pi. If you actually want to see different results every time and want something that's secure, you need to make sure that your random number generator is seeded properly. And so we have this function sRandom, which ensures that the random number generator is seeded. And what you feed into it is some kind of random information that will make sure that the random number generator starts at a different place every time. So in this case, I'm feeding it the current time, because the current time is always changing, and for the purposes of estimating the value of pi, is sufficiently random. Algorithms like this one for estimation are known as Monte Carlo algorithms, and they have two key characteristics. The first is that there is a chance that they are somewhat wrong from the answer that you're trying to get, and they also might not terminate or don't have a fixed termination point. So with our example of calculating pi, we could keep throwing more darts at the dartboard and we could attempt to find a more accurate value of pi by throwing more and more and more darts, and so calculating a better and better and better ratio. And we expect that over time, we are going to get a more accurate estimation for the value of pi. But it's also possible that, we've generated a lot of darts, and by chance, the darts that we've generated happen to be giving us a ratio that's a bit off, because if they're truly random, sometimes that randomness is going to look like a different distribution, even if it's actually drawn from a normal distribution. However, we know from our understanding of probability that if we keep doing this for long enough, we expect the random numbers that we draw to converge to something looking like a uniform distribution, assuming that they are actually being drawn from a uniform distribution. So we have to set for Monte Carlo algorithms after how many iterations we want them to terminate. We can't just let it keep running and running, because otherwise it'll keep running forever. There is another type of randomized algorithm as well, and this is a Las Vegas algorithm. So quicksort is a good example of this when we were choosing a random pivot. Quicksort with a random pivot always terminated. The random pivot was just a selection of where do we start from. And that's still a randomized algorithm. It's still useful to use good quality randomness, but they behave a bit differently from the Monte Carlo type randomized algorithms. And so this difference is worth knowing about, if only to help you categorize the types of algorithms that you are using. So that's all we'll talk about for randomized algorithms. And there is another type of algorithm that's kind of closely related, known as approximation algorithms. Now, while our randomized algorithm for computing pi was also an approximation algorithm, there are approximation algorithms that are deterministic, that don't have randomness built into them. We've already seen one approximation algorithm in our class so far, other than the pi estimation one. This was the cube root function, and I will bring it up on the other computer just as a reminder. This was... So if you recall, we had this method for calculating the cube root of a number inside the computer, even though a computer doesn't inherently have a cube root function built in. And to understand how to generate the cube root of a real number is actually a little difficult. It's not obvious. If I tell you, calculate me the cube root of 2, it wasn't obvious to all of us how we'd go about doing that. And what we ended up doing was using an approximation method drawn from calculus that drew on the derivative of the cube root function to produce an estimation for it. If you remember this function, what we did is we went through a series of estimations. We started with one guess, and we improved on our guess each time. And this is an approximation algorithm because we told the computer, okay, once you get within a certain bound of the true value, stop repeating it. But also, it was not random. If you reran the same process over and over and over, you would still get the same results for the approximation. The core idea for our approximation algorithm was to start with a simple version of the problem, whether that be a simple guess for the solution or some simpler function that you can boil down the more complex problem to, and then iterate on it and progress so that each time your approximation gets a little bit better and a little bit better and a little bit better. There are a number of different examples of problems for which you might want to use an approximation algorithm. A number of examples include numeric integration. So if you want to calculate a very complex integral but don't have a technique to generate a closed form solution for it, you might use an approximation algorithm. These tend to be very, very common in physics, particularly particle physics, where you have complex integrals that represent the state of the system. And then in order to compute the algorithm, to compute the integral, you can either try by hand to resolve it and come up with a closed form solution, quickly finding that we don't have techniques in integration for that. Or you can use an approximation algorithm to generate a numerical representation of what the answer for the integral is over a particular set of bounds. And this turns out to be incredibly useful for practical problems, not just in particle physics, but also in chemistry, where you use similar techniques for quantum chemistry, for which the integrals are too complicated for us to generate a closed form solution. Numerical analysis is the name of the field for solving these particular problems in the instance where what you're after is a numerical solution to the particular problem. Now, approximation algorithms do exist in a number of other places. So very often you might find interesting computer science problems that have very strict bounds. For example, the 3-color problem with the map that we were talking about yesterday has a very strict rule that no two places can have the same color, assuming that they're adjacent. But one might consider relaxing this a bit. One might say, well, on a map, let's allow us to have 1 or 2 violations of this rule, and we'll bound the number of violations of the rule that we can have. So maybe in a map of 50 states, we'll allow 1 violation or 2 violations of the no 2 adjacent matching color rule. It would be an approximation algorithm if we took this kind of problem and said, well, this violation is an approximation to the true solution. And this is another example of where one might use an approximation algorithm if you're okay with having your rule violated, but in a more minor way. We also have 2 examples for us today on where we might use approximation algorithms in concrete scenarios that you can tackle already with the skills that you have. The first of these looks at calculating the differential equation numerically for a damped and forced spring, or in this case, we're just going to look at a damped spring. So a damped spring has some mass, it's some physically heavy object resting on a spring, and the spring is controlled by, or is characterized by a constant k, which is fed into something called Hooke's law that will tell us how much energy the spring will give back when it's compressed a certain amount. We also have some other element C, which is damping the action of the spring. So it's providing some resistance and pushback to stop the spring from giving us as much energy as it would otherwise. And our goal is to figure out what is the behavior of the spring, what is its position what is its position x at any given time t. And for one of these problems, for those of you who haven't solved it before, you can actually set your 0 line for x wherever you like in the problem, but then you have to either go positive or negative in relation to the position of the spring to the location x that you picked. So one convention is to pick x equals 0 as being at the wall where the spring is compressed. So let's see how we might analyze this. Thinking back to high school physics and maths, our acceleration is going to be F equals ma. And so if we calculate all the forces together on this, we have ma equals negative cv minus kx. So minus cv is the damping action that is proportional to the velocity of the spring. That is how quickly the position of the spring is changing as time changes. And then minus kx, that is the force imparted by the spring that changes relative to how much it's compressed. So x is our measure of compression there. For a very small change in time, so if we go from like second t equals 0 to second t equals 0.0001, we can actually use these equations without having to solve the full differential equation to calculate what the change in all our different variables that we care about are going to be. And in this case, we're ultimately aiming to characterize the position of the mass at a given time. So the thing we're going to focus on is x, which is the position. But because in order to calculate changes in position, we need both the velocity and the acceleration, we'll also include those variables. So our acceleration is given by the sum of our forces divided by the mass. Our position is equal to the prior position plus the tiny change in time that we've done multiplied by whatever our prior velocity was. Our new velocity is going to be whatever our velocity was before plus a tiny change in time multiplied by our new acceleration. And then our new time is just going to be our old time plus the tiny change in time. So our delta t in this case is going to be our step size, the amount that we're willing to advance in time. And at the smaller granularities at which you run this simulation, your results will improve. Because we're not solving the full differential equation properly, this is going to be most accurate for small changes in time. This is easier than a full page of math to calculate the solution to the differential equation. So physicists use these kinds of approximation techniques all the time. Let's see how this looks in our code. So again, this is fairly short. The main bit of complex code that we have in here is our graphing function, which is just going to allow us to draw the spring itself. And I'm not going into detail in the graph, but let's look at the actual spring calculation. So we're going to read in some values for x for the initial position, the mass of the spring, and the step size at which we want to characterize the behavior. And then at each step, and this is just making sure that we're within our bounds, because remember, for floating point numbers, if you're not careful about setting bounds, then you're going to start getting floating point errors that creep in, and our simulation either won't stop or we won't be able to tell when our solution has converged. So set a number of points in time for which we are going to output the graph, because obviously we don't want to output the graph necessarily if our step size is 0.0001 of a second. We don't want to output the graph for every 0.001 of a second because we care about the behavior at the spring at a larger time scale. We just want our simulation to run at the small time scale so it's accurate. So this tells the computer to print the graph at some interval that is larger than the actual step size. But at each of the individual steps, calculate the new acceleration, calculate the new position, the new velocity, and the new time, just following the equations that we saw here. Exactly the same thing. Code is fairly similar. So if I run it, it's going to ask me for some arguments. It's going to ask me for the initial position of the spring, the mass of the spring, and the step size, and the step size for the granularity at which I want to run the simulation. So let's try a mass of 1 starting at a distance of 1 and a delta t of 0.1. And let me make that a little bigger. You can see the spring starts all the way out at 1. Then when you let go of the mass, it bounces back in towards the center. It overshoots past the 0 position of the spring out to the other side, shoots back in a bit, shoots forward a little less, and kind of does this zigzagging behavior that you'd expect to see on the spring. So maybe I'll do a physical representation. Let's assume that the 0 position of the spring is over here at the edge of the table here. If I stretch my cell out all the way over here, this is where the simulation starts. I'm a mass of 1 kilo in this thing, and I let go. Boing! I go over here. I bounce back. I bounce back. I bounce back, slowly losing my energy to heat. And if we look at our diagram, this is exactly what's happening with the spring over here. And that is probably the first time and last time that you will see a lecturer acting out as if they were a spring in class. Let's see what happens if we double the mass. I think this was the mass variable. Same kind of thing, but we get a few more jiggles in there. Let's double it again. And as I make it heavier, it's taking longer and longer for the spring to settle down. Now let's see what happens if I improve the granularity here. If I improve the granularity, we still get roughly the same picture, but if I make the granularity much bigger, get a mechanical failure, the simulation's actually not working because the granularity is at the wrong level to be able to predict the behavior of the spring. It might work still at 1. No, let's just keep trying a few values until we find one that kind of works. There we go. So now it's a little inaccurate, but it is working, which shows you the value of choosing the correct granularity for your simulations. Well, it looks kind of pretty. I could sit and watch that for a while. Should we move on or just keep watching the spring bouncing about? Keep watching. Oh, there we go. Okay. Enough watching spring bouncing for today. One of the interesting things about this simulation is it represents the difference between a formal analysis of the situation or a symbolic analysis of the situation and a simulation-based analysis of the situation. And if you're interested in how these examples might play out and give you different answers for a real-world scenario, I'd actually encourage you to watch this super fun video online, which is about simulating a game of Monopoly in an attempt to figure out what the best strategy is for actually winning at Monopoly. Is the best strategy to try and land on Broadway and Park Place and build up the maximum number of hotels there? For those of you who've played a game, once you capture a few squares on the board, you can build up those squares to give you an extra advantage over other players. And so the question is, which squares on the board should you buy, and how much should you build them up? And this is a fairly complex question. It's not immediately obvious how you would approach this. So a simulation seems like a fairly good approach to it, because all you'd have to do is write some code that represents the different squares on Monopoly and that calculates the bank balances of each of the players. Then what you would do is simulate dice rolls for each of the players and give them each strategies for how they would behave when buying properties or not buying properties. Using this technique, you could see, well, if I make player one buy whatever property they land on, whatever square on the board they land on, would this help them? Who would win the game? Would it be the player who goes first? Would it be the player who goes fourth? If you run the simulation 1,000,000 times with 1,000,000 different sets of dice rolls, what happens? There was also someone who attempted to do this similar kind of thing, but actually do a rigorous formal analysis and symbolic analysis of the game and came up with a slightly different result. And this YouTube video here is a discussion of both the techniques that they used to solve this problem of the optimal strategy for Monopoly, as well as the results they found. And I think you'd find it very interesting. This leads us to our last class of, not our last class of class, which it does happen to be as well, but our last type of algorithms that we're going to talk about for today, which is optimization. And optimization is an exciting class of algorithms because many of the machine learning algorithms that I'm sure plenty of you are interested in if you want to do artificial intelligence or anything like that, a lot of the algorithms used in those areas fall into this class. The general schema of an optimization problem is find a function that computes some desirable output y as a function of your input x. Now that seems a little boring. Isn't every function just like that? Well, yes, but optimization treats this in a particular way. One of the key ideas that we would use in a machine learning variant of an optimization problem would be to imitate the real function that is going to generate this output using some model that approximates the goal output on the basis of seeing input examples. What do I mean by that? Well, there is probably some function out there which takes as input a waveform, so the sounds that your voice makes. If you could feed that into a function, there is some function that exists that if you give it how much power was in each different frequency of your voice at each different time, and you feed it into the function spits out a string that tells you what it was you said. Now, this would be a really, really, really complicated function because obviously the process of translating a waveform, a human speech, into text is really difficult. So this function might take pages and pages and pages and pages to write down. If you were going to write down like frequency 100 hertz times 1,000 plus frequency at 500 hertz times 200 plus et cetera, et cetera, et cetera, and then map that to letters, that's going to be really, really complicated. You're going to need to have a lot of parameters. You're going to have interactions between the different frequencies. That's way too difficult. And so the key idea in machine learning is to, instead of trying to figure out that function exactly, if you can come up with a similar function that might be complex enough, and then tweak the parameters inside that function on the basis of examples that you're given, maybe you can approximate that true function in a way that's close enough to be useful. So instead of a function with 100 trillion parameters, maybe you'd have a function with just 1 billion parameters. And then every time you see an example of what the function should do, so one example would be a recording of me saying, "Hello, foundations of algorithms," and then that would be the x. And the y would be hello foundations of algorithms as a string. So that's one example, and you see if the function gets it right. If it gets it wrong, you adjust all the parameters of the function so that next time you do it, it gives you a better answer. So it might not give you the full correct answer, but it'll give you something better. And then you feed in another example. It might be Liam saying, Shannon, you plugged the receiver into the computer, you plugged a transmitter into the computer instead of a receiver. And that would be the recording, that would be the input, and the output would be the converted text version of that. And we then add another example, like Wida saying, excuse me, sir, I don't understand. And another example, and we feed in hundreds and hundreds of these examples, and thousands, and then millions and millions of these examples, and our function starts getting better and better, and our approximation between our model, which has only 1 billion parameters, to the true function, which has like 100 trillion parameters, is good enough that our function starts to be able to convert between these vocal patterns, these sound recordings and their frequencies, into the actual contents of the text. And this is essentially what all of the machine learning algorithms that you use on a day-to-day basis now with Google Maps and Google Translate and, I don't know, Bing this and Bing that, and artificial intelligence inside your iPhone camera that makes the images look better. All they're doing is this optimization process. They're using some function to model the true thing in real life, the true function in real life that's really, really complicated, and then they're using some process to go from examples that are given to a better version of that function. Now, there are other versions of machine learning and AI and other versions of optimization, but I wanted to show you at least this one. The key idea here is what we call gradient descent. Imagine that you are at this point in the mountain and you want to get to the valley. The valley represents a point at which your function is operating better than it is currently. Let's assume that lower values are better than higher values. One example might be, for example, if the value represents the error that your function is generating, then a lower error is better than a higher error. And the question is, how can you tweak your function, or how can you tweak what you're doing to get you to the lower position? So the gradient descent rule is one way of figuring out how to tweak your function so that you can make it a little better. Does anyone have an idea in the last minute of the class of, if I'm up there in the mountain, how I can figure out how to get to the valley, assuming that you can't see, but at every point in time you can take a step in a direction and a little microphone in your ear will tell you your new height? What would be the technique for getting to the valley? Microphone. Bunhao, you're sitting at the edge of your seat. So I'm at this point in the mountain, and I want to get to the valley. I'm blind, and so I can't see the layout of the land, but what I do have is an earpiece, and every time I take a step, it tells me my new height. So what is the strategy for getting to the valley?
So if the height is decreasing, then, the correct direction?
Yeah, so if I take a step, and if the height increases, should I keep that step?
No.
No? Okay, step back.
Yes.
And so what do I do now?
Go to the opposite direction.
Go to the opposite direction, and then what do I check?
Hear the height again.
I hear the height again, and if the height has gone down, then what do I do?
Continue the...
Yeah, I go down that direction. And that's perfect. Thank you, Bunhao. And this is the key idea of gradient descent, is in order to improve our function, we just have to figure out a direction that we can go that takes us closer to the value we want. And in many cases, the value that we're going to be talking about is the error, and we want to minimize the error, so we want it to go down. While I am obscuring some details here, and not every machine learning problem turns into gradient descent, this is really the core fundamental way of thinking about these optimization problems that will help you to at least represent these. And with that, we're on to our last pseudo-strategy, which is not a real strategy, which is adaptation. Modifying some combination of the strategies and algorithms that you've seen before to build the final algorithm that you're looking for. That's it for the core content of understanding how we put algorithms together. Tomorrow, we're going to finish off by looking at 2 last data structures and 2 different types of algorithms as a way of summarizing all of the class, talking a little bit about the future, and maybe a tiny bit about the exam. And that's all for today. Thank you very much, everyone.